happy to be here this year again. And my topic is bypass antivirus dynamic analysis. And 10 years later, I'm going to tell you why in a few slides. So who am I? Emeric Nassi. I founded a company called Baliskit. And my job is to basically write malware legally. So in 2014, years before I created my company, I wrote a blog post called Bypass Dynamic Analysis, where I put down a few techniques to break the emulator system of antivirus. And at the time, it had a lot of traction. And I even found the document in the CIA leak from Vault 7 on Wikileaks. And my goal here is, well, what's the status 10 years later? Are the techniques still working? Can I find new techniques? So first, a few definitions. I want to stress out, when I say antivirus or AV or EDR, I'm talking about the same thing. For me, from an endpoint point of view, there's no difference. And in fact, when I reverse engineered some like family antivirus, I found the same component as enterprise EDR at the endpoint level. So in my opinion, that's a bit of trolling, but in my opinion, when a company sells an endpoint security to a family home or for free, it's called antivirus. When you sell the same endpoint security, you add a bit of monitoring and you multiply the price by 10, you call it EDR. So what we're going to talk about here is in the different detection stages of antivirus. You have at the file analysis level, so when you like right-click analysis, you first have a static detection, heuristic detection. There was a talk about that yesterday. And then you have emulation. So the sample is going to be run inside a sandbox. That's what we're going to talk to today. After that, you also have runtime analysis. There was also a talk about that yesterday. So what's the limitation of dynamic analysis and any antivirus scan? The limitation is the scan has to be very fast. You have to scan sometimes thousands of files. You don't want the user to complain and to switch to another solution. Also, you have to emulate the system correctly, which can be sometimes complex, as we will see. If your sandbox may be detected because it's going to have a lot of specificity. So we are going to attack all those limitations in this talk. So the challenge we have here is we only use simple techniques, no complex techniques that can bring their own IOC detection. So if you add a very complex technique, this can increase the heuristic detection. So we don't want that. We just want a few lines of codes. And I'm going to show a lot of lines of codes, but hopefully it's a simple code, so it should be fine. And I'm testing with C binaries because it's the most scrutinized format by antivirus. So if we can bypass C binary detection, we can bypass anything. Even though I also tested on some script. And I want efficient method, so small method. So just so you know, I did a research on like 20, 30 antivirus plus some online scanners. I checked also antivirus from all over the world. Even some country you do not suspect they have their national antivirus. I cannot share all the names and all this part of the research publicly, but it's there. So how's the setup? So you have a malicious payload. And this payload, you assume it's going to be detected by the heuristic or the signature or whatever. So we encrypt it. Now, because it's encrypted, it's not going to be detected, but the antivirus will run the sample in a sandbox. So it will pass the decryption, and then it will highlight that there's a malicious payload inside, and the antivirus will find it because it's emulated, the encrypted code was emulated. So what we are going to do is this, we have a function called decrypt and launch payload. We know that if the antivirus, the emulator, goes inside there, he will detect the sample as malicious. So our goal is to write an emulation bypass stub before that function to one way or another break the emulation system so the antivirus never detects our sample. So we have 4 types of emulator breakers. We can exhaust resource, we can break runtime implementation, we can attack the system implementation, and we can attack the environment. So let's talk first about resource exhaustion. It's the simplest one. The thing is that scanners, as I said, they have limited time and a limited amount of memory and stuff that they can allocate during the scan. So most commonly, malware will use kind of brute force the decryption key or something to try to exhaust the antivirus and make it abandon the scan. But there are much more easier techniques. So one that I used 10 years ago was just to iterate 1 million times on a variable before calling a decryption launch payload. This used to bypass every antivirus 10 years ago, and now it's flagged. So can you guess what I did? Well, I increment 1 billion times instead. And now it's not detected. So I mean, I could end the talk here. This bypassed all the antivirus I tested. But I mean, we can also find other methods which are more reliable. The problem with this kind of method is that the more your computer gets, the more powerful your computer gets, the more you have to change the method to adapt to the power of the computer. So we can find some methods which do not rely on the power of the computer. Just another example here with a huge malloc. So we are allocating 2 GB of memory. And this also will bypass any antivirus that you have on the market. Because they won't go through the malloc. They will just abandon before they get to the decryption part. So as I said, so exhausting resource, it's quite easy. It works also with other language. But the detection depends on CPU power. So let's try to attack runtime implementation. So first example, attack of the runtime implementation is I attack the random generator. So normally, if you create a seed of 38, you would always have those numbers as the 3 first generated numbers. So you can see if those numbers are the 3 first generated numbers, and if not, that means that you are inside an antivirus which wrongly implemented the run function. This bypasses some emulator, but the good one know how to implement this correctly. Something also I did is attack the heap. So when you allocate memory on the heap, so I allocate a variable, a long variable called content. And I allocated a second variable with the same size. So in the heap, it's going to be organized this way. So first variable, second variable, and you have some metadata in between, like the size of the previous chunk, size of the next chunk. And what I'm doing is, what happens if I call a function pointer from here, minus 24, I should be able to trigger the decryption routine, if the heap is correctly implemented. And this bypassed most detection. I think there's only a couple of antivirus that correctly implements that. So here's the code. It's a bit of pointer arithmetic, but sorry about that. And most powerful things I found is the runtime exception. So you know in Windows you have some specific exception handling called a structural exception handler or stuff like that. So one way to bypass every detection is just to do a division by 0. So you see in this code, I have a division by 0. I have to use this kind of intermediate variable to avoid the compiler shouting at me. And when I catch the exception using the Windows specific exception handler, I decrypt my payload. And this will bypass every emulator. As an alternative in the same method, you can use a filter, so the exception handler. You can pass as a parameter a custom filter. And again, the filter that you pass, you can put the decryption. You can put the decryption method in there, and no emulator are currently able to emulate this. And now, as a gift for you, here's a shellcode loader technique. You probably don't find this in public. So how to turn this into a shellcode loader? So I have my buffer on the variable there. I do a virtual protect to put my buffer as execute read write. I do a division by 0, and in the filter of the exception, I trigger a function pointer to the buffer. So this is a shellcode loader, and it bypasses the emulation engine of the antivirus. So all in one. So to sum up about the runtime emulated part, based on the tests I did, it's really well implemented by a few engines. I did found some bypass method, so especially the exception handling. There's also a bypass on DLL management, DLL forwarding, this kind of stuff, but it's longer code, so it's out of the scope here. So heap runtime implementation is interesting, but let's look at system implementation now. So the Windows system is huge. There's so much APIs and objects and stuff implemented there. So the goal in this category is I'm trying to find a Windows function that is not implemented correctly by the emulator. Function or object. So one way to do that is common in malware, is to rely on parent-child relationship. So you have the process which calls itself, and for example, pass a parameter when it calls itself, or communicate through a name pipe to pass a secret key, or something like that. You can also just check if this process is its own father, and in this case, you will trigger the malicious routine. This generally bypass easily most of the EDR. What I don't like with this kind of solution is you need to spawn a process in order for it to work. And it doesn't work well, for example, if your malicious sample is a DLL, or it works with exec, but it doesn't work well with other kind of format and other kind of use case. So I prefer simpler use case. So we can try to find vulnerability of implementation vulnerability in one of all the available objects in the Windows system. One I tested is a mail slot. Why I tested that? Because I never heard about mail slot before, so I suppose it's not implemented correctly. It's a kind of inter-process communication used in Windows. So here, it's in the same process. I create a mail slot, I put something inside, I read, and I check that what I put inside is the same as what comes out. It bypasses, I think, every antivirus except 2. So it's pretty good, but not perfect. This one bypasses everything. Memory resource notification. Don't ask me what's memory resource notification. I wouldn't even be able to explain. Just, it's a Windows object that's not emulated correctly. So just the handle that is returned is not correct, and just this 3 line of code will bypass every antivirus that exists. Now, so we had a look at Win32 component. What other component can we look at which is very complex in Windows? Well, you have COM. I don't know if some of you worked with COM, you know that it's awfully complex. But in fact, it's quite simple to write a routine that bypasses most emulator. Here I'm just looking from an invalid prog ID and trying to find the UUID corresponding to this ID. So the ID is MCTTP 24. Obviously, I don't have this in my registry base. But most emulator, since this is so complex, they will just always return true. for this function. So if you ask for something that does not exist, you only trigger the decryption of the payload if it returns false. And this bypassed all antivirus except one. Note also, on a side note, COM is great also to bypass detection on script emulators. And it was also very good to bypass MC and other stuff at runtime memory. Okay. Now I'm looking at more hardcore stuff. So it maybe look complex if you don't know C, but in fact it's simple. I'm trying to look at how the NTDLL is implemented. So the first byte of a given function in NTDLL always starts, for example, for a 64-bit process with those instructions. So you move a content of RCX to R10 registry, and then you move the syscall number to EAX, which correspond to this number. So I put a pointer to that place, I grab the bytes, and I say, okay, is it the right implementation that I would expect for this syscall in NTDLL? If yes, I decrypt my payload. And this also bypasses everything except one, because in fact in the emulator, the Win32 DLL are not the real ones, it's just emulated. So that's one way to break everything except one. Another complex method to break everything. So there was a talk yesterday that mentioned this, the PEB, I don't know if you remember. Inside the PEB is kind of metadata that's attached to a process. And in this metadata, you have the list of the loaded DLLs. You see you have those lists. And so what we can do is we can check, is the PEB correctly implemented? And if not, then we're in an emulator. So how I did this, so I accessed the PEB, and then using this complex line, I'm looking at the value corresponding to where the NTDLL module is loaded. And I compare that value to the path that I expect for this module. So the path that I expect should be C Windows System32 NTDLL.dll. And if they are the same, I decrypt the payload. This bypasses every antivirus I tested, because something is not implemented correctly in the PEB. Why? What is not correctly implemented? I know, and I'm going to explain to you later. So to sum up on the system implementation, so what we can say is that all the basic antivirus, so just to be clear, when I say antivirus is good or bad or bypass or something, I'm just talking about the emulator part, the dynamic analysis. I'm not talking about heuristic, in-memory analysis, etc. Just to be clear. Because I had a way to isolate that detection. So, as I said, there's a lot of antivirus who have a very basic emulator, and they're not able to pass those kind of tests. You can find I suggest you find your own bypass. You can just open the Windows documentation, the API, and I think it's a good exercise to do that, to learn about Windows and to learn how antivirus works, instead of just copy-pasting from my slides. There's one antivirus engine that's really good at system implementation, but I cannot give names in public. There's one that implemented correctly almost everything. But yeah, full bypass still exists. So the PEB, for example, PEB implementation with which bypass even that antivirus. So now I want to talk about environment implementation. So when I say environment is the emulated environment, you should have files, you should have a file system, you should have process, you should have everything that you expect on a normal machine should be emulated somewhere. So again, here the perimeter of emulation breaking is huge, because obviously a lot of things will be either emulate wrongly, or you can also find specific artifacts of the sandbox in the environment. So in some sandbox breaking mechanism that you find in malware, they often check for emulator-specific artifacts. I don't really like that method because this is an IOC. If you search for a given artifact, like, I don't know, you're searching, I don't know, for a QEMU process or something, this can be an IOC for the detection that you're looking for that. So instead, what I prefer to do is look for artifacts that should be implemented, but they are not implemented, or they are implemented wrong. It's better for evasion, in my opinion. So you can have a look at files, process, registry, network, a lot of possibilities. I'm just going to show a limited number of samples here. So this one is a very old one. It was already working in 2014. It has been around used by malware writers since 20 years. And the goal is just to check for an invalid URL. So you see here, this URL doesn't exist. I didn't buy the domain. And so you try to open it. And if you cannot open it, then you trigger the malicious routine. What happens is all the antivirus emulation, they do not implement internet browsing. Obviously, you can imagine the implication if they did that. So they will return true all the time when you call any URL. So what a lot of malware writers do is this kind of technique. They call invalid URL, and if the return is true, they know they are emulated or they are in a sandbox environment and they get out. The problem with this technique is that, for a malware writer, is that as soon as a blue team catches the sample, he can register the domain, and then your malware is broken. And I don't know if you remember, but that happened in a real worldwide attack, this kind of scenario. So what else can we check? Well, you know that in a corporate environment, you have some applications that are always there, 99% always there. So you expect to have, if you are on Windows, obviously, you expect to have Office, you expect probably to have Chrome, you expect to have a famous PDF reader and others. So you can just check, are those applications there? And if you are in a red team, maybe you already did some kind of assessment of the target and you know some stuff about the target. Maybe you know they have a specific software installed or something. So you can just look for that artifact. And if that artifact is there, you trigger your malicious routine. Obviously, the antivirus emulator will not emulate that artifact. So that's a great bypass, especially if you know something about your target. So this example, so I'm using files to break the antivirus. So first, I'm looking for a file that should not be there. So I'm looking for a folder called MCTTP in a program file. Why I do that? It's because the bad antivirus emulator always return true for that function. So if they return true for something that doesn't exist, I want to get out. So here I eliminate the bad antivirus emulator. And here I eliminate the good ones. Because the good ones, so they will not return true every time. They will return true only on the files that are emulated in their emulated file system. So I'm looking for Microsoft Office, and if I found it, I decrypt the payload. And this is really good to bypass EDR. I think something is wrong. I think there's one antivirus that is detecting this one now. However, if I use a registry key instead, so for example, I search in the registry for excel.application key, it bypasses every antivirus. Another common method, if you know the name of your payload, if you, for example, then you can bypass anything. So here, in this very small code, I know my malicious executable is called whatismyname.exe. And what I do is, am I called whatismyname? If yes, I trigger the malicious routine. If no, I get out. And this bypasses every EDR. And the reason why is that all the environment, including the name of the current process, the username, etc., is hard-coded in the emulator. So it doesn't correspond to the real name. So that made me think also, if everything is hard-coded, maybe I can, it's the same for all the environment information, maybe it's the same for process, files, everything. And so how can I know more about this emulated environment? I'm not very good at reverse engineer. I mean, I can do basic reverse engineering with Ghidra, stuff like that. But antivirus are a protected process, and it's very hard to reverse them. However, I found a method to black box reverse engineer them. And the best way to know how the antivirus emulates the environment is just to ask the antivirus. So that's what I did. And how do you ask the antivirus? Well, you just create malicious samples. Here's an example. If I want to know if my current file name starts with C:, my current file name pass, I can just check this variable against the 2 first bytes of the current path. And I know that if this triggers a detection, it means that the hard-coded value starts with C:. If it doesn't trigger a detection, it doesn't start with C:. And this way, I can brute force letter by letter all the value from the emulated environment. So here's a few examples on the default antivirus, the Defender. So you see, like for Defender, and this is on every machine. If you test on your machine, you will have the same. So the current process is always cmyapp.exe. The current user is always John Doe. And the current computer name is always Al990H. This is on every Defender endpoint. You have those values. I also obviously did the test for a lot of other antivirus solutions, but I cannot give the names in public, so I just keep with the default one. So just those examples show that you can brute force anything from the environment system based on the black box method. And everything is hard-coded, so the name, the domain, environment variable, file system. And so you remember the PEB implementation? So I brute forced the PEB implementation for Defender. And so that's what I got. So I got a value that's really close to the right one. So it is implemented correctly. I have the path to NTDLL. But there is a difference between the expected one and the one that's simulated. They didn't put the capital letters in the right place. So that's why you have the bypass, because the PEB emulation had the capital letters wrong compared to the one you have in the real PEB. So that's the kind of thing you can find with the black box emulation. Something else, environment variable. So first, and this is true for any antivirus, a lot of them are not implemented at all. And some of them are implemented but incorrectly. So if you see, for example, for Defender, if I brute force the value of app data, the value is C document, which, I mean, this folder even doesn't even exist on a machine. And you have also a lot of variables which are just not implemented. Even public, which is used in a lot of malware, it's not implemented. So what kind of letter that lesson we learned from that? So we can exploit what we know from this kind of reverse engineering to create samples. So here, for example, I create a malicious screensaver. So it's spoofing a PDF. I spoof the PDF icon. I spoof the PDF extension. but the extension is .scr. So it is screensaver. But in fact, it's just an exe that I renamed .scr, and it works the same. I don't know if all of you are aware of that, but exe and scr are the same format. And what do I do to bypass emulation in this case? Well, I just check. If I'm ending with exe, then I get out. Because my sample ends with scr, not exe. But since it's going to be emulated as myapp.exe or something like that, game over. I can bypass every antivirus using that. I can also check for the non-implemented environment variable. So here's an example how to do that. So I look for the OS environment variable, which normal value is Windows NT. And so, for example, this works on Defender because OS is not even implemented. So I don't even have to check against the expected value. I can just check if I have a positive return to the call. And if yes, I decrypt and launch the payload. And this bypasses every antivirus also. We're checking for some unimplemented variable. So to sum up on the environment implementation, so you see that some are really easy to implement, and compared to, for example, exhausting resource, they are maybe more reliable, and it's much more difficult for the engine to implement correctly all of those values. And if you know something about the target, then it's game over. If your target has a specific software installed, you can just check for that, and you bypass the emulation. So I found that some antivirus implement a few counter against brute forcing. So by implementing randomization. So there's one antivirus, for example. If you check for the current process name, it's always in C downloads, and then it blocks because the name is randomized at every launch. But I mean, it's not very good because C downloads doesn't even exist on the normal system, but it's still better. It's still a kind of improvement compared to others. We are soon going to go to the end of the talk. Before that, so a few sad findings during other research. So in 2024, you still have a lot of antivirus that do not detect samples in 64-bit. Like, imagine the same sample, 32-bit is detected, 64-bit is not detected. Sometimes I also find the reverse. So this is for the static detection. A lot of antivirus do not implement dynamic detection or implement just a very limited one. So maybe they can bypass the basic encryption, but if you add anything before that, they get lost. It doesn't mean they are not good, because they can be very good maybe at other stuff like heuristic detection or in-memory detection. But for the emulation part, some are really, really good. I can give you the name later if you come talk to me. And some are not existent. I also found out that some free endpoint protection are better than some very expensive ones. Again, I cannot say publicly which ones. And yes, some are way above others. As a final thought, doing this kind of research, the hard part is to isolate the emulated part from the static or heuristic detection. Sometimes it can be very tricky because, like, I add a dynamic bypass stuff, and then I get detected. So I say, oh no, they implemented that in the emulator. But no, it's just that the code I added triggers a heuristic from the static part. So it's quite tricky to isolate every component of detection. So yeah, I said the detection set can be misleading. And also, when I discussed with the researchers, I already had this discussion with someone who's very, very good, very good security researcher, and we were discussing that he had to add like very complex indirect syscall mechanism, etc., to launch his payload because he was detected before. And he thought that he was bypassing in-memory detection. But in fact, I showed him, no, it was just that the fact he added the syscall, he was not detected by the heuristic detection, but that's it. And he could keep the same function without even calling syscall and maybe adding a dynamic bypass stub or some other stuff to break the static analysis, and then he would not get detected anymore. So yeah, it can be very confusing if you're not aware of all these steps. You can think something is detecting you, and in fact, it's something totally different. So I want to thank you for your time. So as I said, I cannot give public names, but you can come to me after the talk if you are curious about the antivirus ranking that I have. You can reach out also if you want by email or X or LinkedIn. And if you have any question, feel free to ask.